When you have to make solutions, there are two ways in which you could do that. One method of making solution involves using pure solute and pure solvent, determining the amount of solute needed to make a certain volume and a certain concentration of a solution, and dissolving it, the solute, the required mass of the solute, in enough pure solvent to create that volume and that concentration solution. For example, if you were to make a salt water solution, you would start out with pure salt, figure out how many grams of salt you would need to have a certain volume, certain concentration solution, and then add to that required quantity of water and mix the two together to make a homogeneous mixture. So that is one way of making solutions. The calculations with respect to this method of making solutions, we dealt with that in the previous session. But there's another way of making solutions as well. For example, if you go to one of the wholesale club stores like Costco or Sam's and you buy one of these, let's say a liquid cleaner, concentrated liquid cleaner bottles. When you need to actually use that at home, you can't use the original solution, the original liquid. By the way, the original liquid that you bought is not pure either. That original liquid is a solution itself, except that it is extremely concentrated. Its concentration is quite high. But when you have to use that liquid at home for a certain cleaning job, you would have to take a certain quantity of that concentrated liquid and add water to it in order to decrease its concentration, in order to dilute it, and then use the diluted solution. So the second way of making a solution, which is quite often used at home as well as in the laboratory, is dilution. Dilution is a procedure by which involves adding solvent to an already existing solution with the goal of lowering the concentration of the original solution. You probably may have bought these concentrated juice mixes that grocery stores sell as well. Once again, that's a concentrated solution. It's not pure substance at all. But when you have to consume it, you have to pour that into a pitcher and add a required quantity of the solvent, which in that case is water. Mix the two together and make a diluted version of that solution, which is now ready for consumption. So this is called dilution, whereby a solvent is added to a higher concentration solution in order to create a new solution that has a decreased concentration. Just as making a solution itself is a physical process, dilution is also a physical process because the chemical identities of the solute and the solvent are not changed in this process either. Upon dilution of a solution, the concentration of the original solution always goes down. Dilution implies lowering of concentration by addition of the extra solvent. So the volume of the solution goes up, but the concentration of the solution goes down. So just again to re-emphasize, dilution is a procedure of adding solvent to an existing stock solution with the goal of lowering its concentration. It is a physical process because the chemical properties of the solute and solvent are unchanged, and upon dilution the concentration of the original solution goes down, whereas the volume of the solution is increased because of the added solvent to that solution. So when you're looking at a dilution process, we have to understand that let's assume that there are two solutions. A stock solution. Stock solution is the original solution, the solution whose concentration is higher. So let's assume that its concentration is M1 and its volume is V1. If you know M1, the concentration of the stock solution, and V1, the volume of the stock solution, can we calculate from these two numbers the moles of solute in this stock solution? Let's call it moles 1. Absolutely. I mean, if you remember from our previous session, molarity is equal to moles divided by volume in liters. If that's the case, how do we calculate moles of a solute in a solution? Equals molarity times volume. So if the molarity of the stock solution is M1 and volume is V1, then moles 1 equals M1 V1. I hope that makes sense. Okay, so number of moles therefore of solute in the stock solution will equal M1 V1. Now when the solution is diluted, we create a new solution let's call it diluted solution, and let's call its molarity M2 and its volume V2. Remember that during dilution process, M2 is decreased, the molarity is decreased, so M1 will be greater than M2, but volume of the diluted solution goes up because we are adding solvent, so V1 is less than V2. Okay, but using the same analysis, that if M2 is the molarity of diluted solution and V2 is volume of the diluted solution, then the number of moles of the solute in the diluted solution equals M2 V2. Now here's a question that you need to answer before we move on. When we dilute a pre-existing solution by adding solvent, do we change the number of solute moles in that solution? Absolutely, you're right. No, we don't. The only change that is made is to the volume of the solvent and therefore the total volume of the solution. But we do not make any change to the moles of the solute from the stock to the diluted solution, which basically means that the number of moles of solute in the stock solution equals the number of moles of the solute in the diluted solution. So these two properties will be equal because no change is made to these. If that is the case, then M1 V1 will equal M2 V2. In other words, number of moles of solute in the stock solution will equal the number of moles of solute in the diluted solution. Now this is a formula that applies only for dilution processes where a concentrated solution is diluted by adding solvent, and which is a physical process. Please memorize this formula, this equation, to be used in problems such as this. Now in this problem, we are taking 35.7 mLs of a stock solution and it is diluted to a final volume of 500 mLs and a concentration of 0.075 molar, and therefore what is the concentration of the original solution? Please remember this is a dilution process, therefore M1 V1 equals M2 V2. If you notice that if you read the problem carefully, you will realize that V1 is 35.7 mLs. That's the original volume. The final volume is 500 mLs, and the final concentration of the diluted solution is 0.075 molar. If you plug in the values that we know into this equation, the only unknown left is M1, or the molarity of the stock solution. So by rearranging the equation, we can solve for M1, which comes out to be 1.0504201,681 molar. This answer needs to be rounded to two significant figures because of this concentration right here is in two significant figures, and when rounded to two significant figures, the answer comes out to 1.1 molar. In other words, the 1.1 molar original solution, 35.7 mLs of it, was diluted to the new solution. Okay, so let's try out a few more problems of the same kind. Once again, remember that in dilution problems, the equation that works is M1V1 equals M2V2. Okay, now let's see what we have, what information is given to us. Calculate the volume of a solution prepared by diluting. So which volume is this? Is this V1 original volume or V2 diluted volume? Exactly, this is V2 because it is prepared by diluting it. So we are diluting 125.0 mLs of 1.80 molar. So which volume is 125.0 mLs? Exactly, that's V1. 1.80 molar solution is therefore the original concentration, and this concentration is lowered to M2 equal to 0.555 molar. Okay, so if M1V1 equals M2V2, how do we calculate V2? V2 will be equal to M1V1 divided by M2. Let's plug in the values that we have. We know V1 equals 125.0 mLs. M1 equals 1.80 molar divided by final concentration 0.555 molar. Notice that in this case, the units of volume do not need to be changed to liters. Why? Because it's a ratio, and whatever unit you have on one side of the equation needs to be the same as the unit on the other side of the equation, but it doesn't necessarily need to be converted to liters. Molar and molar cross out, leaving behind an appropriate unit for volume. When you finish this calculation, we get 405.405454 mLs. This needs to be rounded to 3 significant figures to 405 mLs as the diluted volume. Okay, let's look at the next problem. Once again, please pause the recording while you read the problem and you try and set it up. So in this problem, what information are we given? We are given V1. We are also given the corresponding molarity M1, and we are given the final diluted volume V2, and we are asked to calculate M2, the final concentration. So if you remember, M1 V1 equals M2 V2 for dilution, that means M2 equals M1 V1 divided by V2. Once again, plug in the numbers, the data that is given, 6.50 molar times 25.00 mLs divided by 125.0 mLs. Once again, notice mLs cross out, so therefore we don't really need to convert it into liters here. And when you solve this, we get 1.3 molar. Now, is this the correct final answer? No, it's not. The final answer must be in 3 significant figures. Even if your calculator gave you 1.3, you cannot leave it as that. You do need to express it in 3 significant figures, in this case by adding a 0. The next problem gives us similar information. It gives us, first of all, the next problem, please pause the recording, read the problem, and then we'll discuss it together. The next problem is also like a dilution problem. It's not exactly a dilution problem. Let me explain to you what I mean. It is a dilution problem in the sense that it's not a chemical process. It's a physical process in which you are mixing 2 solutions. Here is solution 1 and here is solution 2. Now, how do I know that it's a physical process if you're mixing two solutions? Are all two solutions when mixed give us physical process? No, that's not the case. This is a physical process because if you notice, the solvent and solute are the same. The solvent is water for both of these solutions. The solute is potassium hydroxide for both of these solutions. So if I'm going to take the same solutions and put them together, would I have a chemical process take place? No, exactly. There's nothing to react with. All you're doing is mixing. All you're doing is a physical process. So that is why I said it's something that is like a dilution process. So in this case, let's pictorially explain this before we move on. Here is solution 1. We are taking 0.500 liters of this solution of concentration 1.25 molar, and we are adding it to solution 2, 755 mLs of it, concentration 0.850 molar, and by adding them we are creating a new solution 3. Now, um, let's say that the volume of this solution is V3 and concentration of this solution is M3. Now, if I took, hypothetically, if I took 20 ml of a salt solution and added it to 30 ml of another salt solution, same salt, same solvent, what would be the total volume of the final solution? Exactly, it would be 50 mLs because 20 mLs plus 30 mLs, they are both the same things. If I took 20 mLs water and added to 30 mLs water, I would get 50 mLs water. So similarly, since the solute and solvent are the same in both of these solutions, V3, the final volume of this mixed solution, will be the sum of the two original solutions, V1 plus V2. In other words, 0.500 liters and plus 755 mLs. So in a way we do know V3. M3 is the one we need to calculate. Now let's pay very close attention. If you know the volume and concentration of a solution, can we calculate moles? Yes, we can. We've done this before. Moles will be equal to concentration times volume, meaning that we can figure out the moles of the solution in this first solution. We can figure out the moles of solute in the second solution. If I take X number of moles in the first solution and add it to Y number of moles in the second solution, can I calculate the number of moles in the third solution that is created by mixing the two? Absolutely, you can, because moles of the solute in the third solution will be equal to the sum of moles of the solute in the two solutions that were mixed to each other. Okay, so with this knowledge, how would I calculate number of moles of solute in the third solution? Exactly, V3 times M3 will give me moles of solute in the mixed solution. So, can I say M3 times V3, which is moles of solute in the mixed solution, equals M1 times V1, that is the number of moles of solute in the first solution, plus M2 times V2, which is the number of moles of the solute in the second solution. Okay. So, do we know if that is the case, can I say M3 equals M1 V1 plus M2 V2 divided by V3? Yes, we can, exactly. So, let's now plug in the numbers because we have all of these numbers. Please remember V3 equals V1 plus V2. Okay, so let's plug in the numbers. M1 is 1.25 molar. V1 is 0.500 liters plus M2 is 0.850 molar. Now the volume of the second solution is given in mLs, so we can convert this into liters. That would be, so 0.755 liters divided by V3, which is 0.500 plus 0.755 liters. Okay, if you solve this, you would get 0.625 plus 0.64175 divided by 1.255, which then gives us 1.00936255 molar, because liters will cross out, leaving behind molar. So the concentration of the mixed solution is this, but this needs to be rounded to 3 significant figures. Therefore, the final answer, or the concentration of the solution created by mixing the two given solutions, will be 1.01 molar.